Hello everyone, I am Dr. Clement, Research Assistant Professor working at the Department of Chemistry, SRMIST, KTR campus. Today I will discuss one of the most interesting topic, that is characterization techniques for nanostructures. In this module, I will introduce different characterization techniques used to analyze the nanostructures and understand its properties. Here the list of techniques are displayed to characterize the nanostructures. The first, the most important one is X-ray diffraction technique. The second one is scanning electron microscope and transmission electron microscope and scanning tunneling microscope, atomic force microscope. These are set of techniques comes under microscopic techniques, and then we'll move to the spectroscopic techniques, which is X-ray photoelectron spectroscopy, and then BET analysis, which otherwise called nitrogen adsorption desorption analysis, and at the last thermogravimetric technique. So these are the set of techniques available to characterize the nanostructure, to understand the structure and properties. I will start with X-ray diffraction technique, for which Sir William Henry Bragg and Lawrence Bragg received Nobel Prize, and they are a very famous scientist in UK, and Sir William Henry Bragg is the father and his son name is William Lawrence Bragg, and they worked in the Sir William Henry Bragg worked in London University, and then Lawrence Bragg in Victoria University in Manchester. So this is the father, and here is the son, and this is the Bragg family, lived in UK and contributed immensely in the field of diffraction studies. Now let us start with the basics. To understand the X-ray diffraction analysis, we should start with crystalline solids, that is solid state chemistry. There are 7 crystal systems, as you all know, and the respective informations are given in this table. I'll briefly introduce the 7 crystal system. The reason is we are going to use the X-ray technique to understand to identify and understand these crystal system. The first one is cubic. The possible variations are primitive, body centered and face centered. And the second important one is tetragonal, which involves primitive and body centered. And third one is orthorhombic, which is primitive, body centered, face centered and end centered. And fourth one is hexagonal, which is primitive. And the fifth one is rhombohedral or trigonal, which has primitive. And the sixth one is monoclinic, which is primitive and end centered. And the seventh one is triclinic, which is primitive. So now these 7 crystal system shows the possible variations. And the interesting thing is the axial distances or edge length and axial angles and respective example. Let us go one by one. Say for example, if I take a cubic, in the cubic these are the 3 variations are available. In that, all the edge length, say for example, A is equal to B is equal to C. Similarly, alpha is equal to beta is equal to gamma is equal to 90 degree. That is called the axial. And the best example for this system is sodium chloride and zinc blend, even the copper. So similarly, you can check the tetragonal. In the tetragonal system, there are two variations are available, namely primitive and body centered. Here, only A is equal to B, but B is not equal to C. Meanwhile, alpha is equal to beta and beta is equal to gamma, which is equal to 90 degree, which is this angle of axis. You can look at this simple cubic system and understand what is angle of axis. This is alpha, this is beta, this is gamma, and this is the edge length called A, and this edge length is B, and this edge length is C. So you understand every system from this simple cubic system. So when we understand this simple cubic system, we understand all the crystal system. So these are the lattice parameter of every crystalline structures we can calculate using the X-ray diffraction analysis. The most interesting parameter is A, which is called edge length, and D means D space, and third one is the Miller indices plane, which is HKL planes. All these lattice parameters also can be identified using the X-ray diffraction analysis. Now let us just take one more example and try to understand. Say for example, let us take orthorhombic. So if the solid structure belongs to the orthorhombic, then these are the possible variations are available, namely primitive, body centered, face centered, and end centered. Here the interesting thing is the edge length are not equal. So in this case, the A is not equal to B, and in turn B is not equal to C. Whereas alpha is equal to beta and beta is equal to gamma and gamma is equal to 90 degree, which means the actual angles are all 90 degree. And the best example for such a system are rhombic sulfur, KNO3 and barium sulfate. So likewise, you can take any example and try to understand the actual distance and actual angles and the respective examples. All my suggestion is you start with the simple cubic to understand the crystal system. Now, how this X-ray diffraction works, the basic instrumentation. To understand the working principle, we should understand what is X-ray, and then this how X-ray and sample interact. That's called X-ray sample interaction. And the third one is the Bragg's equations. So if we understand one by one, then we will understand the instrumentation part very clearly. Now we will try to understand the instrumentation, the basics. The as I said, the instrumentation, in the instrumentation part, the X-ray sample interface, the interaction is very important, and this image clearly tells you the possible way of interactions. Say for example, when we pass the X-ray, that is called the incident radiation. So what are the different possible phenomena that can occur? Namely reflection. If the X-ray hits the sample and gets back to the original state, it's called reflection. And there is a transmission possibility, which means the sample can penetrate through, that's called transmission process is observable. Sometimes the X-ray can be observed, that phenomena is called absorption, and sometimes it will get refracted, that's called diffraction or refraction. So here we can see the different possible phenomena that can occur when we pass the X-ray on the sample: reflection, absorption, diffraction, scattering, and diffraction. So all these phenomena are possible. So now the thing is, when diffraction takes place, at what condition diffraction will take place, that is the most important thing. So to understand that only, Bragg equation is very important. So Bragg equation says when Bragg law is satisfied, then diffraction occurs. All other these phenomena is not important. So that is the most important aspect we learn from this slide. Now this is the instrumentation part. So here we can see this is the X-ray source, and this is the primary X-ray optics, and this is the goniometer, the most important part of the instrument, and this is the sample holder, and this is the detector, and here one more key aspect is that's called collimator, that's called diffracted beam is analyzed here. Here in this instrumentation part, the key role of goniometer is very important. This goniometer, which is which is here, measures the angle of X-ray sample and detector. So when X-ray strikes on a sample and it reaches the detector, the angle of incidence will be, that is called the 2 theta value, right? So that can be measured using the goniometer. And the other important thing is, it, the goniometer rotates the sample holder in a well controlled manner, so that we can rotate the sample and make sure that X-ray strikes on every part of the sample, every part of the crystalline structure. Yeah. So here we can understand how this X-ray strikes on a sample, which indeed connected with the goniometer, and how it reaches the detector. So this is the X-ray source by which we can pass the X-ray, we can hit the sample, the X-ray strikes on a sample and it interacts with the sample. After that, it reaches the detector. Now we can calculate the 2 theta value by using the goniometer. So by understanding the 2 theta value, we can also find out the intensity. So that is how we get the diffractogram. So this is the a typical XRD pattern of NaCl crystal, by which we can understand what is the x-axis and what is y-axis. Y-axis is the intensity of diffracted X-ray, and x-axis is the diffraction angle, that's called 2 theta, and this is the X-ray diffraction pattern. So in this X-ray diffraction pattern, we usually assign these pattern with Miller indices. That is nothing but the HKL plane. So in the next few slides, I will explain few more steps to understand the X-ray diffraction, and then later I'll explain how to calculate this HKL plane in detail. Now this is the most interesting aspect, how this XRD machine works. That is the detection of diffracted X-rays by photographic film. Now let us just look at this. So this is the sample, correct, and then which is circulated by the photographic film, because when X-ray strikes on the sample, the diffracted X-ray has to be recorded using the photographic film. That is the key aspect in the instrumentation. So this is the point where incident beam enters. So through this small slit, the X-ray passes through and it hits the sample, and then after that it gets diffracted, and the diffracted X-ray will be recorded using the photography. The most interesting thing is the diffracted X-ray will make a conical shape uh, X-ray. So say for example, that's D by Sharer camera is used to measure that. The sample of some hundreds of crystals, that is porcelain crystals, shows that the diffraction beam form a continuous cone. This is what is important. This forms a continuous cone. A circle of film is used to record the diffraction pattern, as shown in this image. Each cone, very important, each cone, say for example 1, 2, 3, each cone intersects the film, giving the diffraction line. That's it. So this is how the diffraction angle is measured. So this is the beam of entry and this is the beam of exit. Now I would like to introduce uh, 4 key steps to understand the working function of XRD. The first step is the X-ray beam is directed to the powdered sample, where it is collimated to ensure that it hits the sample at a specific angle. So the X-ray beam diffraction analysis is the first step. Second, the X-ray are diffracted at a specific angles when the condition of Bragg's law is satisfied. So after some times I will explain what is Bragg's law, and here you should understand the second interesting thing is the X-ray are diffracted at specific angles when the condition of Bragg's law is obeyed. And the third is the intensity of the diffracted X-ray is measured as a function of angle theta, creating a diffraction pattern. The position of these peaks in terms of 2 theta relate to the lattice spacings, while the intensity of the peak is related to the number of planes. Once again, let me read this. The position of these peaks, which is that is called the 2 theta, relate to the lattice spacing, while the intensity, which is y-axis, is related to the number of planes contributed or number of planes available in the crystal system. Now, the principle, how this Bragg's law works, and why the Bragg's law has to be satisfied for the diffractions to occur. Correct. So let us try to understand these illustrations. Say for example, this is one plane, this is another plane. So this is X-ray 1, this is X-ray 2. Let us try to understand. So X-ray 1 passes through a sample and gets diffracted. Easy, right? And X-ray 2 also strikes a sample and then it gets diffracted. So now let us label these X-ray 1 and X-ray 2. So I say for example, this is the point of incidence light, which is called a Z. So here now the trigonometric in a trigonometric mathematic way, we will understand how this diffraction works. This this is labeled as A, this point, and this point is B, and this point is C, and the distance between the two planes is denoted as D. That's called D spacing. Correct. So this is the theta, right? So now we know what is A, what is B, and then what is C, and then what is Z. Now let us take this angle, that is ABZ, that is ABZ, this ABZ, this part ABZ. So here the n lambda, that is the X-ray that we pass through, that is equal to AB plus BC, that is AB plus BC, AB plus BC. AB is equal to BC, of course, right? So n lambda is equal to, if we substitute this BC with AB, then it is called 2AB. Correct? Yeah. So we know for trigonometry, as per trigonometry, sin theta is equal to AB by BZ. That is AB by BZ. That is adjacent by opposite. Correct? Yeah. No, adjacent by hypotenuse. Correct? That is AB by BZ. Therefore, so sin theta is equal to AB by BZ is nothing but D. This BZ is equal to D. We can substitute D. So therefore, AB is equal to, this D goes to the left hand side, D sin theta. Now let us substitute this AB here. So n lambda is equal to this 2 multiplied by AB means D sin theta, that is 2D sin theta. So theta is equal to 2D sin theta if n is equal to, if order of reflection is 1. So theta is equal to lambda is equal to 2D sin theta. Theta is basically works based on HKL pens. So this is how Bragg's law is derived. And the last important aspect is how this diffraction occurs. When n lambda is equal to 2D sin theta and n is equal to an integer, how waves reveal the atomic structure of the crystals. So the diffraction occurs only when Bragg's law is satisfies the condition for constructive interference from the plane with spacing d. So there are two types, constructive and destructive. This is constructive, means X-ray 1 and X-ray 2. So when the incident beam, that is the lambda is equal to 3 angstrom and d is equal to 3 angstrom, when these two matches, this diffraction occurs in a particular way, that's called constructive interference. Then I will quickly introduce what is this constructive and destructive interference. So constructive interference occurs in this pattern. Can you just look? So in a space, if all the wave X-ray goes like this is called constructive. If the pattern, if the X-ray pattern changes, then this is called destructive interference. Note This is very important to note that the constructive interference is very important for the diffractions to occur, while the destructive interference will not lead to the diffraction. So that is the condition. So the concise key points with this, I'll wind up XRD working principle. So the fixed wavelength is very important. That is, the wavelength of X-ray is typically fixed, which is around 1.54 angstrom. And the variable angle during X-ray diffraction experiment, the angle of incidence theta can be varied. Matching the D spacing means that as you change theta, the equation from the Bragg's law, that is n lambda is equal to 2d sin theta, allows for different interplanar spacing to satisfy the condition for which constructive interference occurs. And the last key point is constructive interference. At a specific angle, constructive interference occurs for various set of crystal plane that corresponds to different D spacing. Therefore, by adjusting theta, we can effectively find the appropriate d theta value in the fixed wavelength of X-ray, that leading to the observation of diffraction peaks. So with this, I'll wind up the XRD working principle, and in the next class we will discuss how to calculate the HKL.